In the last module, we looked at arcs, which are parts of a circle, and their relationship with the angles that are intercepting them. Here in this module, since we started to talk about circumference in the last lesson, which is basically the length around the circle, in this lesson we're going to talk about arc length, which you could consider to be the distance along an arc. So in part A, we are first finding the circumference of the circle, and so we know the formula is 2 pi r. We substitute 9 in for r, and we get that the circumference of the circle is 18 pi. So in this problem, we're trying to find the arc length of AB, and we're told that the measure of arc AB is 60 degrees. So since an entire circle is 360 degrees, the arc length will be 60 out of 160, or 1/6 of the circumference. And that word "of" means that we're going to be multiplying. So we're taking 1/6 of 18 pi, and when we multiply that together, we get 18 pi over 6, which is equivalent to 3 pi. And they want us to go ahead and evaluate that, so we get our handy-dandy scientific calculator out, and we multiply 3 times pi, and we get 9.42 centimeters. So the arc length of AB is 3 pi, or 9.42. So how could we use that reasoning process that we used in the last example to find the length of an arc of a circle if the arc measure is m degrees? Well, what did we do with the measure of the arc? We put it over 360, and we multiplied it by the circumference. And so you see that that's the formula we have here for arc length. And arc length is abbreviated as S. Don't ask me why. But there's our formula for finding arc length. It's just a fraction of the circumference. Here we're given that the minute hand is 6 inches long. The reason why they're giving us that is the radius of the circle. And it's asking us how far does the tip of the minute hand travel as time progresses from 12 o'clock to 12:30. So 30 minutes over 60 minutes is 1/2. So the central angle formed is 1/2 of 360, which equals 180. And use the formula for arc length. So it's m times 360 times 2 pi r. The arc measure we already saw was 180 times 2 pi times 6. So that's 1/2 of 12 pi, which gives us 6 pi. And they want us to evaluate it, so we're going to take 6 times pi in our calculator. And 6 times pi is 18.85. So the length of the arc is 18.85 inches. In this example, they're asking us to consider a set of concentric circles, and the radius of those circles is increasing 1, 2, 3, 4, etc., and that the central angle is 90 degrees. So it's asking us to find the arc length based on what that radius is. So they found the first one for us. Here's what they did. 1/4 of 2 pi r. And when they multiplied that together, they got 1.57. So what if the radius was 2? Then the arc length of S in terms of pi would be, well, it'd be 1/4 of 2 pi times 2. So that would be 1/4 of 4 pi. That would be 1 pi. which is approximately 3.14. What if it was 3 pi, or the radius was 3? Then it would be 1/4 of 2 pi times 3. That's 6, so that would be 6 pi over 4, which reduces to 3/2 pi. So I think we see a pattern developing here. This would be 2 pi, this would be 5/2 pi. So let's evaluate that in our calculator. And 1.5 times pi is 4.71. 2 times pi is 6.28. 2.5 times pi is 7.85. I copied and pasted that table onto this screen to make it easier for me to graph these points. And I'm graphing the points r, s. So when my radius was 1, the arc length was 1.57. When the radius was 2, s was 3.14. When my radius was 3, s is 4.71. Four, 6.28, and 5, 7.85. And what do we notice about the points? They are forming a line. And what type of relationship is the relationship between the arc length and radius? This is a direct variation. And I know this is a big throwback to Algebra 1, but in a direct variation, you have an equation y equals kx. And k is what we call the constant of proportionality, constant of variation. They're asking us for the constant of proportionality in this relationship. So let's think about what this equation was. It was S equals something times R. Notice what is always being multiplied by R. It was the m over 360 times the 2 pi. In part B, we're converting 60 degrees. So 60 pi over 180 is pi over 3. So that's what they've done here. They just have a few more blanks filling in. In Reflect 5, they're asking us to explain why the radian measure for an angle m degrees is sometimes defined as the length of the arc cut off of a circle with radius 1 and central angle m. Wow, that's really wordy. All right, so let's break it down. If I were to convert that m into radians, if my radius of the circle is 1, well, let's think about what the arc length would be. It would be that arc measure over 360 times 2 pi times 1. Well, this would just simplify to m pi over 180, which you may recall is exactly how I defined the whole conversion process of converting degrees into radians. Explain how to find the degree measure of an angle whose radian measure is pi over 4. Well, pi over 4 would equal m pi over 180. And I'm trying to find m, which is the degree measure for the angle. If I multiply both sides by 180, I get rid of all of my fractions, which is good. 180 over 4 is 45, so I would have 45 pi equals m pi. Divide both sides by pi, and m is 45 degrees. Convert each angle measure to radian measure. So 90 pi over 180 would reduce to pi over 2. Oh, hey, this 45 looks kind of familiar. We saw it back here. It's pi over 4. We know that 360 degrees is the degree measure that corresponds to a full circle. What is the radian measure that corresponds to a full circle? Let's work it out. 360 pi over 180. That simplifies to 2 pi. So there are 2 pi radians all the way around a circle.